Welcome to Drone Systems and Control course. In this particular lecture, we are going to talk about recurrent neural network for trajectory prediction aspect of it. In the last lecture, we talked about what's essentials of neural network. We talked about the building blocks, and we talked about multi-layer perceptron and how you can find the weights. We did not go in details of the learning algorithm, but we talked about how it can affect the performance when you have if you don't select the architecture properly, what we call generalization ability or overfitting, underfitting aspects of it. Think of it, if you are flying a drone and you are collecting a data for a motor propeller. For a different RPM, we have a different thrust information, right? And let's assume that you are building an advanced drone where you can not only control the RPM, you can also control the pitch of the propeller, right? Then you have two different input. For a different combination of the input, the thrust produced and torque produced will be different. The relationship between the RPM and the thrust is a nonlinear function. I can approximate directly the relationship. Right? I can do an inverse approximation also. If I want a specific thrust, what should be the specific RPM I can get, right? I can do the inverse function. Based on the data we can approximate, right? And we can use that neural network for a given thrust, what's the RPM needed, right? We can calculate even that. But what we are going to focus more is on GPS denied navigation perspective. Autonomy is one aspect, right? When there is no GPS signal, we don't get the position information. We need to estimate our position accurately, right? We need to predict my XYZ coordinate or global coordinate frame if I want to put a latitude, longitude, right, and height. I want to predict that information. Only I don't have a GPS, but I have my IMU present. I have my altimeter present. With that, can I use any neural network to predict the position accurately for the given input? Right? Then we can use that for a navigation purpose. For this, recurrent neural networks are important. Okay. Lecture 34 objective. Why do we need recurrence in neural network? Right. Understanding the temporal data. Remember, drone is a dynamical system, right? When you give an input, a specific command to a motor, right, or all four motors, right? I want an RPM to be changed from 1000 to 1200, which will change the thrust, right? Which means that drone will have a specific performance, right? It might climb from one altitude to another altitude. All four motors are changing the RPM equally, right? If there is a variation based on that, the motion of the drone will be different. That's a temporal data. How do we understand this temporal data? And then we look at definition of a recurrent neural network. What is the difference between the feedforward and recurrent neural network? What are the challenges, right? And how one can use tap delay phenomena to represent this temporal data and still use a feedforward structure of a multi-layer perceptron or and then represent the temporal data for trajectory. Or we can look at very special network called memory neuron network, which is very unique. We will be focusing more on that and then see how we can implement that particular architecture to predict the output accurately, right? Then we talk about trajectory prediction using memory neuron network. Why do we need recurrence, right? What is a feedforward neural network? Let's try to understand the feedforward neural network. Then we can look at why we need a recurrence. What feedforward neural network does? It has an input feature X and it has an independent output Y, right? And it finds a functional relationship between X and Y. Right, that what I mean, y can be expressed as a nonlinear function of x, y is equal to f of x kind of a thing, right. No sequential relationship when we talk about feedforward neural network. Means the past input and output does not affect the current output. Means a previous time step just before the current sample. I have given an input and I got an output from the network, and those two are not going to affect my performance at all, right. Whereas if you look at a recurrent neural network, on the other hand, the output y depends on the current input x, past input x of t minus 1 and y of t minus 1 also, right. There is a sequential relationship. Past input and output do affect the current output. You can use recurrent network for trajectory prediction, system identification, control, sequencing, and so on and so forth. If I am trying to represent the architecture, right. So if I see y equal to f of x is what we are talking of here. If I say here y of t is function of x of t minus 1 and y of t minus 1, right. That is what we are talking of as a recurrent neural network, right. So if I am just trying to represent the architecture, let us say there are two input x1, x2, right. Then I have a 3 hidden neurons and 1 output neuron, right. So I am connecting all the inputs, right, to all the neurons in the hidden layer. This is input, this is hidden, and this is output, right. If you look at here, it is a typical feed forward structure. The data flows from input to hidden and hidden to output. The current input x1 and x2 will affect the output y, right. So if I have to write this in a form, y is a function of x1, x2 and the w is the parameters, that is a weights in the layer. If I am going to represent the recurrent neural network for a similar architecture, let us say x1 and x2 are there, then I have to think of the previous input. This is x1 of t, this is x2 of t, right. This is x1 of t minus 1, x2 of t minus 1, right, and those are inputs. I could have hidden neurons, right. Then I have an output y, and I can put y of, this is y of t minus 1, right. Basically I am talking about there is a delay, and the delay comes back here, right. Here again there is a delay. I can think of putting a unit delay, which is usually represented as z power minus 1, and that is your x of x1 of t minus 1. Similarly, you can put a delay, and that is your x2 of t minus 1. You see here there is a feedback mechanism. You can ask question, why only one output, why input? The number of passed value depends on order of the system, which we will talk about it later. Okay. Now let us understand the temporal data, right, how this temporal data can be represented. Let us take a dynamics of YA subsystem, right. We talked about the YA subsystem in module 2 as well as module 3, right. R dot is function of R, omega d, Vd and theta d. The omega d dot is again another function f omega, R, omega d, Vd and theta d, right. Let us say I am giving a step response for a unit yastic change, right. How do we capture the temporal nature of the data, right. If I am just giving a step response, I am looking at yaw rate to just change, right, some new value, right. So just changing and going all the way to 0.4 degree per second or radians per second, depends on the unit that what we are looking at over a period of time. This is the temporal data that we are talking of, right. Now, how do we represent this temporal data when you look at the samples, every samples? At t is equal to 0, the input goes to the yaw subsystem is u naught, the output come from the yaw subsystem is y naught, right. At t is equal to 1, sampling time instant 1, right, and not 1 second, sampling time instance 1, u1, y1. You can do all the way to un, yn. This is a time, right. This is how the data is represented. Data is sampled at every instant, sampling instant, and represented in this fashion, right. Now, if you look at a temporal data, what happens is at t is equal to 0, u naught is an input, y naught is an output, and there is a hidden state h naught which is passed on to second sampling instant, which define the change in state, right, the current state of the system on which the input u1 is applied, right. Similarly, you can go on. This is how the temporal data is represented. Every time instant, sampling instant, this current state will be given as an initial state to the next time instant, and using that initial state you will get a response, right. This is how we represent the temporal data, okay. That is a temporal connection between one instant to another instant, right. Now, mathematically, if I wanted to represent this, right, I am looking at every instant. If I wanted to see, my mathematically y is equal to a function of u and h, right. So, y is the output of a yaw subsystem at any instant, could be 0 or 1, 2 or anything, right, and it is function of u input, h is the hidden state of the subsystem, right. So, what will happen, the initial when you give u naught time t is equal to 0, h naught is 0, system is in equilibrium condition, and equilibrium condition we are approximating here 0 0 0. So, that is why I do not have explicit representation of h naught here, okay. Sorry, not h naught, h here, right. Now, there is a famous theorem called Billings theorem. The Billings theorem state in general, the input output model of a dynamical system can be written as y of k plus 1, the response of the system at k plus 1th instant is function of yk dot 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 all the way to y naught, xk all the way to u naught, right. Now, there is another theorem in neural network which people often use called universal approximation theorem, where I can use a single hidden layer neural network with a sufficient number of hidden neurons required to approximate the nonlinear function. In the we can use k passed, that is uk to u0, k passed to the system, and output of the system, k is the order of the dynamical system here, right. So, let us look at the difference between a feed forward and a recurrent neural network, right. A little bit more clear understanding of feed forward neural network. It has an input layer, it has a hidden layer, it has an output layer. The inputs are distinct states x1 to xn. These are x vector x, n dimensional vector as an input. You can have hidden layers v1, v2, vc. There are c neurons in the hidden layer, and then you have an output y. Y is again a function of v1, v2, vc. If you see a recurrent neural network, I am just giving a different representation of the same, right. If you, I can connect this easily for you to understand. Let us say x1, xm, the external inputs to the system. You have y1, yn are the hidden states, and y1 is your output, what you are looking for. All the n states, right, are fed back here. Now, if you remember the temporal data what we have shown earlier, right, you have input x, you have output y, and then you get your H naught. This is your H naught, right? And that goes to the next time instant. This is X naught and Y naught, and then you have X1 and Y1, right? The next time instant, whatever the input at time t equal to 1 sampling instant, and that is your input. The previous state H naught is what you have, right? You see it nicely represent the temporal data, okay, and this is one such recurrent neural network. I have shown one more neural network in few minutes back, right? I have one feedback inside the input layer, one feedback from output layer to hidden layer. That is also a recurrent neural network. As long as you have a feedback loop in the structure, if you look at here, always the input flow from one to next layer. Whereas if you look at here, the input flows from output layer to the input layer with the delay, right. So, this is your recurrence, right. This particular architecture is useful for sequence prediction. If you are talking about genome sequence prediction, or if you are talking about protein sequence prediction, or you wanted to predict what is the probability of appearance of head or tail based on the past observation data, the recurrent neural network will be useful. Or if you wanted to represent a physical system, right, like drone, aircraft, or any robot, all these are physical system which changes with respect to the states, which changes with respect to time, and then you can represent them nicely using recurrent neural network. Now let us understand the difference between feed-forward neural network and recurrent neural network, right. A recurrent or feedback neural network, we can use any name, right. Feedback is basically a recurrence, that something is fed back from next layer to the previous layer, right. So if you look at a feed-forward neural network, the connections between neurons are single forward directional, right. It is suitable for function approximation of a nonlinear functions which can map the input and output relationship very effectively, right. You can use it for classification problems, you can use it for function approximation problem like what I mentioned, the RPM versus thrust. You want to approximate using feed forward neural network, you can just simply do it. For a given RPM, there is one specific thrust, right. The RPM change to some other value, there is a different thrust you can get. That relationship nonlinear, but that is not dynamical, right. So I can use that. The advantage with this feed forward neural network, there is no stability related issue. Moment you have a feedback, right, the stability aspect comes into picture. If the feedback is negative or positive is very important, that could lead to stability of the network, right. So that issue is not there. It is a powerful tool for any approximating any functional relationship, and it can be used for classification kind of a problem. Those who are interested in to know more about neural networks, they should pick a course in deep neural network or neural networks and its applications. There are various courses are there that will help them to understand in details. Because this particular course focus more on autonomy, one particular aspect for us to do autonomy is to operate in GPS denied environment, which means we need to estimate. We are talking about intelligent way of estimation. So it is just kind of an overview kind of a lecture, right. More detail, one should take a proper full course on that. The recurrent neural network on the other hand, if you look at connections going to happen between neurons in bidirectional, it could be forward as well as backward, right. It is suitable for approximating dynamical systems, sequence predictions, right. It is suitable for predicting financial stock prices in the next time instance or t step ahead, what is going to happen for the energy price, or whether we can predict workload or load, electrical load prediction. All those are possible with recurrent neural network. Here, because you have a bidirectional flow, stability is always an issue. It is a very powerful tool, when you talk about trajectory prediction, when you talk about system identification, control and memory, recollecting something with a partially lost information, recurrent neural networks are most suitable for that, right. We will focus more on one particular architecture which we will be using it for trajectory prediction, right. That is nothing but memory neuron architecture. It is similar to feedforward neural network, but it is very unique in its characteristics. The recurrence is inbuilt in a way that memory present in every neuron capture the past information, right. The white circle is the network neuron, is a normal neuron what you see in feedforward neural network. For every neuron there is one memory neuron associated with that, right. That memory neuron stores the past information that helps the approximating the effect of past states in predicting the current value more efficiently, right. The input layer network neuron has one memory neuron, whereas if you go to the output you can have more than one memory neuron, and they will contribute how the past values, how many past values that you wanted to directly take, and that can influence your output immediately, right. Now let us understand how this network neuron and memory neuron are connected. If you see here, there is an input goes to your network neuron, and the output of the network neuron is scaled by a constant alpha and passing through a delay, unit step delay or unit sampling delay, and goes as an input to a memory neuron. The output of memory neuron is multiply 1 minus alpha, goes through a delay, and that becomes an input, right. If you see, it has the effect of the current input, effect of past inputs in a exponential decay kind of a form, right. So this represents nicely the effect of the pass in the network, right. Let us say we will understand a little bit more in how they function later, right. The connections between network neuron and subsequent layer in one directional, except there is only one feedback present in the memory neurons, otherwise there is no feedback in the main architecture, right. But there is a feedback in the memory neuron on the output layer directly to the input. There is a recurrent loop here, right, which helps me to approximate the function. It is a very unique architecture. There are a lot of variations available. There is something called LSTM, long short term memory, right, and one can use that also, but it is not the scope of that particular lecture. So we will just stick to one architecture, explain and how we use it and demonstrate. Okay. Now you want to understand more about this, you can go and read this particular paper, right, memory neuron network for identification and control of dynamical system, which was published in 1994. It is a very classical architecture which is widely used for system identification and control related problems, is extensively used in flight control. So that is why I thought I will just pick up this particular architecture and explain, right. Now let us understand how the memory neuron works, the functioning aspect of the memory neuron, right. So let us look at general network neuron, okay. So x11 of k is an input which goes to the structure, right. What you get output of the network neuron is S11 of k, right, first network neuron, right, and then V11 of k, right. I am trying to represent, V represents the output of the memory neuron, S represents output of the network neuron, right. S11 of k is nothing but x1 of k. So the input goes just like that without any modification, right. The output of the memory neuron V11 of k is alpha 1, right. This particular alpha 1, this is for the first neuron, so it is alpha 1, S11 of k minus 1. This is S1 of k, because there is a unit delay step, S11 of k minus 1 plus 1 minus alpha 1 1 of V11 of k minus 1. So, there is again a delay. Now, just think about it. If alpha is equal to 1, what will happen? If alpha is 1, this particular term will become 0, which means there is no effect of the past, which means the current input and immediate past input is very important, right. If alpha is very close to 0, what does it mean? The memory neuron plays a very important role than the immediate past, right. So, this alpha is a learning parameter. So, based on the data, based on the error gradient, this particular alpha is learnt and decide how my past relationship is going to affect my output V11 of k, right. So, it will determine in turns the effect of the past to approximate the dynamic relationship, the temporal relationship present in the network, right. This particular one alpha 1 1 is called first memory neuron weight in the first layer input, right, input layer. Now, let us try to understand the first input neuron itself, right. For the simplicity I am taking a 2 input 1 output system, okay. So, we will understand the functioning of that with the 2 input 1 output, okay. I am going to focus more on to the input layer. This is, and single hidden layer network is what we are going to focus. This is input and this is hidden and this is your output, okay. I am just taking 2 inputs so that it is easy for us to understand this, right. The output of the network neuron, right, S11 of k is x1 of k, output of memory neuron is V11 of k is alpha 1 S11 of k minus 1 plus 1 minus alpha 1 V11 of k minus 1, right. Whereas 1 1 represent that connection goes from the first memory neuron to the first hidden neuron, right. And alpha 1 is the memory neuron weight for the first layer, right. Now, let us look at the second neuron, right. There are 2 input neuron. So, S21 is nothing but x21 of k. The output neuron V21 is alpha 2 S21 of k minus 1 plus 1 minus alpha 21 V21 of k minus 1, okay. That is for the input layer. This alpha 2 is second memory neuron weight in the first layer, that is input layer, right. Now, let us look at the first hidden neuron, right, this particular neuron, okay. Let us try to understand the output of the first hidden neuron. S11 of k is whatever the input comes to the network, which is called H1 of k, right. The input goes to this particular neuron, right, is called H12 of k. The output is S11 of k. What is H12 of k? Is a nonlinear function of W11 S11. This is the weight W11 times S11 plus W12, right. This is the second neuron. This is W12 S21 of k plus F11, that is a memory neuron weight. These two corresponds to network. These two corresponds to memory, okay. You see here this V11 and F11 corresponds to this particular connection, right. And then that is basically what we are talking of F11 P11. Then if you look at this particular connection, right, is what F12 V21, right. So, how all the 4 inputs are added and then you have an activation function, You can use any activation function, it could be sigmoidal or bipolar sigmoidal. One can choose an activation function, and that is your H12 of k, right. Then the output of the memory neuron, this particular neuron, the output is given like this: V1 of k, 112 of k is alpha 12 S112 of k minus 1 plus 1 minus alpha 12 V112 of k minus 1. It is same as if you look at the structure is similar, but the parameters are different based on which layer it is representing, right. The 2 represent the second layer, the superscript 2 represent the second layer, right. The subscript 1 represent the first memory neuron, right. S11, S stands for the network neuron output, 11 means first memory neuron's output, right, at k minus 1, that is what it represents. Okay. Remember, superscript represent the layer, whereas the subscript represent the neuron, which neuron it is, right, the first neuron or second neuron or kth neuron, like that, right. Let us look at the last hidden neuron, right, and let us understand the equations, right. I am assuming this is going to be the mth hidden neuron, right, and the output coming from this mth hidden neuron is SM1 of 2 represent the second layer, right. The input to the hidden neuron is HM2 of k. Okay. Now what is H2M of k? If you look at WM1, so basically this is the network neuron, right, this is WM1, 1, right, and this, right, is W, this particular link is your WM2 of 1, right. This is the connection what we are talking of, right. Now if you see the bottom portion, this is a memory neuron connections, basically a link from the first memory neuron to the network neuron, from the last memory neuron to the network neuron is represented by this, right. So all the network neuron receives input from memory neurons as well as from the network neurons, whereas if you look at the memory neurons, right, it will receive only from its own network neuron as well as self feedback, right. The output of the memory neuron, if you see, this is from SM11, this component is coming from the network neuron, right, whereas this component coming from self feedback. Okay. So that is where you get your V2. Okay. Now let us try to understand the output coming from the neuron in this particular layer, right, the output of the last layer, right, output of output neuron, whereas I call this input and this is an output layer. So output neuron SK, right, output, because I have one output I just use SK as it is, H13K, right. This is the first layer, second layer, third layer, 3 represent the layer, this is first layer, this represent the second layer and this represent the third layer. The superscript 3 represent which layer the neuron is. Okay. The subscript represent whether it is a first neuron, second neuron, third neuron. Because we have only one network neuron, right, I just put H1 of k. Okay. What is H1 of k? If you see here, this particular neuron receive inputs from the network neurons, okay, that is the first row. Then the memory neuron in the previous layers, That's your second row. Then you have the memory neuron in the third layer itself, feeding it to the top part with the feedback of beta. That's your third row, right. You see here the output neuron has a very special structure. It has a feedback structure here. It's taking its own memory neuron output as an input to the network neuron. Okay, that's why H13 has a unique structure. If you look at this, you can have every layer network neuron has only one memory neuron, whereas in the output layer you have more than one. You need to understand that equation also, right. Let us look at the output of first memory neuron, and this output is V113, right. The 1 represents the first network neuron and first memory neuron of the first network neuron, that is why it is V11, and 3 represents the third layer, right. It has H13 of k minus 1 plus V113 of k minus 1. Now this is V123, right. V123 of k depends on alpha 1 to V11 of k minus 1. Here there is a delay, right. This is V11 of k, this is V12 of k. So there is a delay, V11 of k minus 1 plus 1 minus alpha 11 V12. If you see the difference between these two neurons, first neuron receives the input from network neuron, whereas the second memory neuron receives from previous memory neuron. Okay, that's the understanding you should get it. So you see the structure is nicely built to capture the effect of pass, and the parameters is learnable, right, because it's learning this alpha and beta based on the data. It identifies how many pass values are required to approximate. Let us say if this alpha 1 2, right, is 1, then there is no effect of this, right, as I explained earlier, right. So you understand immediate pass plays an important, this alpha is a weight. Remember, these alphas are always between 0 to 1, right. It's strictly greater than 0, it cannot be negative. I don't want negative. Moment I have a negative, the instability comes into picture. So these alphas are restricted between 0 to 1. Moment I restrict the alpha between 0 to 1, I can ensure the stability of the network, right. That is the first thing. Now you can ask a question, how am I going to do that? Because when I do the update, alpha can be negative or alpha can be greater than 1. What shall I do? There is a simple philosophy, right. This is a circle in which alpha could be, right. So anything greater than 1 will be projected immediately back inside the circle, right. So the weights of memory neurons are restricted between 0 to 1. This alphas are restricted between 0 to 1, not the beta, right, not the beta. This is not restricted, it can be negative, it can be positive, whereas this alphas not only for output neuron, all the memory neuron weights are restricted between 0 to 1. Okay. Now what we did in this particular lecture, we talked about what is recurrence, why recurrence are needed, what is the difference between a feed forward and feedback neuron, how we can represent the temporal data, right, how the connections established from one sampling instant to second sampling instant. We talked about different representation of feed forward and feedback or a recurrent neural networks, and we looked into one specific recurrent neural network called memory neuron network. We took a simple example of 2 input 1 output system. We discussed about how the input and output connections, how the function of it. In the next lecture we talk about the learning algorithms for these tunable parameters, and then we talk about how we can use it for simple trajectory prediction problem. Thank you.